Hi there. In this video, we'll look at problem 23 on page 194 from section 4.1, which is all about finding maximum and minimum values for functions. Just a quick overview of this topic in general, and then we'll look at this particular problem. We're meant to find extreme values and where they occur. And general idea here is that extreme values can only occur in certain specific ways. Firstly, at a point where the slope of the graph is 0. Secondly, at a point where there's no tangent line, and we call those two categories critical points. And secondly, if your domain is restricted, then it's possible that your maximum or minimum values could occur at the endpoints of the interval. Okay, so with that, our general plan to attack these problems is, number one, find the endpoints of the domain. If there are any endpoints to be found, we'd like to get them. Number two, find the critical points. If any critical points exist, we'd like to get those as well. And thirdly, we're going to plug each of those special points into the function, get the outputs, and choose the highest and lowest values. And with that, let's go ahead and get started. Okay, first thing we'd like to do is figure out the domain. We know that the square root function likes positive numbers. We can do square roots of positives. It's fine with doing 0. The only thing that can go wrong is if we try to evaluate the square root of a negative number. And as long as we're talking about real numbers, we know there is no real answer to this problem. Okay, so summarizing, the quantity under the square root sign has got to be 0 or higher. Has to be bigger than 0 or equal to 0. Okay, variety of ways to continue. I'll just factor this expression. And I'm going to omit some of the details. Follow up on this with me if you want more of the details. But if you plug in 1, for example, for x, so let me just take out x and put 1, then you're going to get 0 times 2, which is 0. So that works. 1 works. If you put negative 1, you get negative 2 times 0. That works. And if you plug in any number that is higher than 1, say 2 or 22 or 2 million, you're going to get two positive numbers, and when you multiply them together, the answer is positive. So anything out here in this direction is fine to plug into this function. All right, in the same way, if we plug in a value that's lower than negative 1, let's say negative 5, you're going to get the product of two negative numbers, and two negative numbers have a positive product, so you're allowed to plug in any values to the left of negative 1 into this function as well. The only thing you can't do is plug in a value that's in between these two numbers. For example, if you try to plug in 0 or 1/2 or negative 0.33, you're going to end up with one negative quantity and one positive quantity. And when you multiply them together, the answer is negative. The square root function won't have it. Okay? So with that, the domain of the function is 1 to infinity, as well as numbers in the interval from negative 1 to negative infinity. Okay, and normally we write that left to right, so let me just be standard here. Oh, I think it was standard after all. And there you have it. Okay, so that lengthy analysis, let me just state the conclusion. The domain of the function consists of numbers from negative infinity to negative 1, as well as numbers from 1 to infinity. Okay, there you have it. Let's go ahead and just take a peek at the graph so that we can see that really is true. Inputs 1 and higher are associated with points on the graph. Okay, 1 and higher. Inputs that are negative 1 or lower are also associated with points on the graph. If you look in between, you see no graph at all, because those are outside the domain. Okay, so just checking our work, and let's continue from there. Step 2, this is the calculus step. We would like to know which inputs are critical numbers. If there are any, you'd like to find them. And so we're going to take the derivative. But in order to do that, I'm just going to rewrite the problem as a power. Knowing that the power rule is just simple to apply, I like to use it whenever I can. Okay, so let's bring the power down to find y prime. 1/2. And let's decrease this by 1. 1/2 minus 1 is -1/2. And we get this expression right here. To make it easier to understand, I'm going to write it as a square root in the denominator. And that is our slope formula for this function. Okay, and we would like to simply figure out, are there any points that make the slope equal to 0? Are there any points where the tangent line doesn't exist, where the slope does not exist? Okay, so let's explore. Okay, to start off with, let's see what happens if I put 0 for y prime. Putting 0 for y prime, just to see what happens. Okay, and I'm just going to erase this because it's done its work. So we won't bother about that anymore. Okay, if the slope is 0, then we should be able to multiply both sides by this quantity right here. And we get 0 times whatever equals 1. Well, that doesn't make any sense. So what that's telling me right there is it's impossible to make the slope 0. There just aren't any horizontal tangents for this graph. Okay, so let's back it up to like it was. Are there any points where the derivative doesn't exist? Okay, well, let's analyze the form of the derivative. Form is 1 over stuff. And is 1 over stuff ever undefined? Well, of course. If the denominator is 0, then the slope is undefined. So let's ask ourselves, is there some value of x that will make the denominator equal to 0? And just by inspection, we can see that if you put 1 in for x, you get 1 squared minus 1. That's 0. Square root of 0 is 0. Times 2 is 0. And you can also tell if you plug in -1, you're also going to get 0. And if that didn't occur to you, you could simply solve when does the denominator equal to 0, and you will get these answers right here. Okay, so we do have, in fact, two critical numbers, two critical points, two inputs that make the slope undefined. So let's go ahead and summarize our work and state our conclusion. Okay, we want to list the candidate inputs for the maximum and minimum, and those would include the endpoints in the domain. So the graph has an endpoint here. Okay, really there's two branches to this graph. So there's an endpoint here and an endpoint here. And then normally we would separately list critical numbers, but it just so happens the critical numbers for this function are identical to the endpoints of the branches. So we don't have any additional candidates for the maximum and minimum. And now what we want to do is actually substitute these values into the formula and see what outputs are produced. So we get the square root of something squared minus 1. If we plug in 1 as an input, we get 0. And if we plug in -1, we also get 0. Okay, so if this function has a maximum or a minimum, then it's got to be 0. And that's about all we can do at this stage. We need some other tools to really complete this analysis. But the graph is showing us that, indeed, 0 is the minimum. And we can see that this graph confirms our analysis. Let me go one step further, though. I'm just going to graph the tangent lines at 1 and at -1. And you can see the graph actually has vertical tangents at 1 and -1, which is why they're critical points. In fact, the graph does have a slope. It's just that, or does have a tangent line, rather. It's just that the tangent line has a slope which is undefined. In some sense, it's infinite slope. Okay, so there we have it. Let me state the conclusion very clearly. Our analysis suggests that 0 is the minimum value of the function, and the inputs that produce that minimum are -1 and 1. And that's the answer to this problem. Hope you found that helpful. See you next time.